Turning this back on and switching back. Projector's still on, hopefully. Come on, tech. So we've discussed a few ideas to do with atoms. That was just to see how much you guys knew, and you knew already, okay? Basically what I've said, but there's a few things I want to make clear. So we established that we got the protons, the neutrons, and the electrons. And the protons and the neutrons are in the nucleus. In an element, okay, all of the atoms have the same number of protons, okay, in an element, right? The way we define an atom is by the number of protons it has. If carbon had an extra proton, it wouldn't be carbon anymore. It would be nitrogen. All right? Now you'll notice that that number corresponds to the number in the periodic table. Exactly, the atomic number. There are about 112 different elements, and they can be made into new elements inside nuclear reactors, as I said before. But each element has its own symbol. In the symbol, the first letter is always a capital, and if there is need of a second letter, they give it a lowercase. You should have seen that before in year 10. All right? So if we look at sodium, it has an atomic number of 11 because it has 11 protons. Its mass is actually somewhere in the magnitude of 23. Its average mass is 23 because it has 11 protons, but it might have 12 neutrons. And the mass of the protons and the neutrons, the mass is equal to the protons and neutrons added together. All right? And we'll practice that later on. But just for now, I want you to understand when we see these weird symbols, they have meaning, and the numbers have meaning, and where they are has meaning. And if you can figure that out, you've done almost all your work for you. So what we're going to we're going to decode this table. Yep?
Isn't it if the same number of protons is the same number as electrons?
The same number of protons is the same number of electrons. Is that always the case?
No.
When is it not the case? Not quite isotopes. It's when we form ions.
No,
But you're right. As a basic element, basic neutral, okay, the protons will equal the number of electrons. But the moment you lose an electron, you can still hold on to your protons. All right? Isotopes, you mentioned there, they have the same number of protons but a different number of neutrons. You've heard of the Springfield isotopes? It's the baseball team in Springfield, like in The Simpsons. You know why they're called the Springfield isotopes? Yeah, because they're sponsored by the nuclear power plant. So, Springfield isotopes, what that means is an isotope is something that has an imbalance of neutrons or a different number than a regular atom, and usually they end up being radioactive. Excuse me. They end up being radioactive because the nucleus is unstable. There's too many particles there. Okay? So isotopes of elements have the exact same chemical properties, it's just their mass is different. A different number of neutrons changes the mass, and this will affect the physical properties. For example, the melting and the boiling point. So if you want to get isotopes, certain isotopes of water, there will be a slightly different melting point depending on the mass of that atom, and then you can harvest that and use it to enrich your uranium if you feel like making weapons. Try not to do that because we don't like it. So, for example, tritium is an example of a isotope of hydrogen. It has 1 proton and 2 neutrons. Tritium is used in fusion reactors. Uranium-238, all right, has extra neutrons than uranium-235. Uranium-238 was used on Hiroshima. Uranium-235 with plutonium was used on Nagasaki. They were trying to test the difference and see if it was worth it. They used different mechanisms, though. So, I think it was the plutonium, but that was dependent on the trigger mechanism. They used a core trigger, like an all-around core, where they fired it from every different angle. The uranium-238 just used a standard gun barrel trigger. I'll go into nuclear weapons later, but I mean, I shouldn't. But I like talking about it. It's interesting, if not terrifying. But isotopes, again, I'll say it again, same number of protons, same number of electrons, different number of neutrons. So, dividing it up, when you get a symbol or a chemical symbol, you'll have, so for example, I've got C and I've got a 12 here and a 6 here. The atomic number is the smallest number. In this case, carbon is the atomic number 6. The big number is the mass of 12. So the atomic number is number of protons in the nucleus. Each element has a different atomic number, obviously. The mass number is number of protons plus the number of neutrons in the nucleus as well. All right? Yes. And those different types of carbon can be used to detect where brain activity is failing or if it's overstimulated. So what happens is they give you the radioactive isotope of carbon embedded in sugar, because sugar is a carbon-based compound. And then once they've given you that, it'll go through your system. And where your brain is active, you'll see it's processed the radioactive carbon. And some places where it's inactive, you'll see an abundance collection of that sugar, all right, where nothing is working. And they can actually look on the photograph and see where the black spots are based on where the radioactivity is. Okay? So and another way of using carbon isotopes is carbon dating. Exactly. The half-life. Okay, so radioactive material break down. So if you get a core sample from the Antarctic in the ice, you have a look at how much carbon is in there, factor of the carbon-13 or whatever, and that'll tell you how old. You compare that with something to see how old it is. Okay? That's based on core samples from the Antarctic, and then you compare it with like a pot you might have found in your backyard to see how old that is. But yeah, by how much carbon has degraded in it. All right? But that's, yeah. Oh, it's starting again. Okay. I'll go through this and then leave it to you guys to start writing some notes down, and we'll have a bit of question time. So, the atom, for example, here I've got hydrogen, atomic number 1, mass number 1, number of protons must be 1, therefore its number of neutrons is 0 in ordinary hydrogen. Number of the electrons, 1. Carbon, so we talked about C12 and C13, C14. Carbon 12, 6 protons, because it's got an atomic number of 6. Its mass is 12, so it must have 6 neutrons. Whereas carbon 14, which is a radioactive isotope, it's the same element, same chemical properties, different mass, which means it's got a different number of neutrons. Okay. Chlorine, obviously, chlorine is 17 on the periodic table, 17 protons. It's got a mass of 35, therefore it has 18 neutrons. I don't think I need to go any further with that. I think you understand. Yeah? Cool, cool, cool. I'll stop that record.